Today I've got three main kinds of problems that I want to work through. One is a problem about finding the population of a city that's shaped like a circle. Now, most cities are not shaped like circles, but I think there's a few planned cities here or there that are. And so, it's a decent exercise in trying to understand how you might use calculus to do such a thing when you know how the density depends on the distance from the center of the city. Second kind of problem I want to do today is finding centers of mass. In some other situations, more complicated than one-dimensional objects. We'll look at two-dimensional and a three-dimensional object. And then the third kind of thing I want to do today is introduce the idea of the work done by a force. I was hoping for more time for more complicated examples today, but we didn't have time for that in the first class, so I won't have time for it for you guys as well. On Friday, we'll do more complicated examples. So let's start with this problem that you see here. Number 19 in section 8.4, circle city, a typical metropolis. And by the way, that's a joke, right? Not circles. Cities are not typically shaped like circles. And even if they are, they're not typically having a constant density at a constant radius from the center, which is what this is implying. It's densely populated near the center and it gradually thins out near the city limits. In fact, the population density is 10,000 times 3 minus r people per square mile at a distance r miles from the center. This is a strange city, not a typical city. Part A says, assuming the population density at the city limits, at the edge of the city is 0, find the radius. That's supposed to be easy. What would it be? Can you just look at that and tell me? 3, yeah, that's when that density is going to be 0, when r is 3. Part B is to find the total population. That's the harder part. You've got to set up and then do an integral here is the idea. So once again, let's make a drawing. Here is Circle City, shaped like a circle. Once again, well, I could choose a coordinate system with the origin at the center and axes going in certain directions, but I really don't need to worry about the axes here. Effectively, just worry about the origin. Think of the center of the city as the origin. The radius of the entire city is 3 miles. That's the answer to part A, right? That's where the density, the population density is 0. Let's go ahead and write the population density here, over here to the right. I could call it delta of R to be consistent. Delta of R is 10,000 times 3 minus R people per square mile. I do, before solving this problem, want to delve into a little bit about what this means. That is half the battle if you're really trying to understand what's going on here, is understanding what this means. And then when you understand what it means, it helps make the rest of the problem make more sense. So let's do that right away, actually. Let's think about what it means. Imagine you're at an arbitrary distance r from the center of the circle. The problem says this population density only depends on r. In other words, it's constant when r is constant. It's constant along circles centered at the center of the city of radius r, where r is fixed. But what does that mean? Well, let's just pretend r is, well, in this picture here, what does it look like it might be? Close to 2. Let's pretend it's like 1.8. What is delta of 1.8? That would be 10,000 times 3 minus 1.8. 10,000 times 1.2. 12,000. Oops, that's supposed to be a 12,000. 12,000 people per square mile. What is this telling you? It's telling you that if you are on this green circle here, our radius, pretend is 1.8 from the center of the city. Say you're right here. And you consider a small area near that point. Emphasis on the word small. What kind of area, what kind of region? Does it have to be a circle, a square, a triangle? It doesn't matter. It could even be a blob shape, as long as it's small. To keep it simple, make it a square, because it's easier to think about areas of squares. Imagine a small square of area, how about call it delta A, near that point on that circle of radius 1.8. What this fact is telling you is that the approximate small population in that small area is delta of 1.8 times the area. That would be 12,000 people per square mile times the area, delta A, square miles. And the square miles would cancel, and you'd be left with units of people. So for example, if the small area is 0.1 square miles, which try to imagine 0.1 square miles, the square root of 0.1 is close to 0.3, because 0.3 squared is close to 0.1. Square root of 0.1 is about 0.136. Imagine a square whose sides are 0.316 miles. Can you imagine that? Can you imagine 0.3 of a mile? Maybe a place near your house. Maybe the block near your house is 0.3 of a mile. Here on campus, maybe if we went from here to the SRC, that might be about 0.3 of a mile. So imagine a square with that side length. That would be a square of area, 0.1 square miles. And this would tell you the population in such an area would be approximately 12,000 times that, which would be 1,200 people. Of course, to fit 1,200 people in such a region, there'd probably need to be some apartments. So they're not just all on ground level, right? There's some apartments with varying number of stories. And this approximation, this density function up here is going to be a good approximation to the population density if these approximations here get better and better as the areas get smaller and smaller. Now, it would take a very, very planned city in order for such a population density to be very accurate. So this is some made up example, completely made up, for the purposes of understanding concepts and learning how to set up integrals, which again is the main skill you want to get out of this, is how to set the integrals up. Solving the integral and finding the answer is kind of beside the point almost. The more important thing is setting things up. That's the skill you're going to need in your science and engineering classes. And even economics, if you take advanced economics classes, for example. All right, now let's go ahead and find the population. So I want to generalize what I did here. At an arbitrary radius r, okay, I want to generalize it in two ways. One way I want to generalize it is an arbitrary radius r instead of r equals 1.8. Another way I want to generalize it is I don't want to think about small regions like that with small area near that point, but in fact, small areas whose, circumference is kind of big. I want to think about thin rings. Because I can still do this kind of approximation multiply delta of r times delta A because for a small ring or a thin ring like this, R is approximately constant. And delta of R depends on R. That's why this kind of approximation would still be good. The area, first of all, of the thin ring, washer, if you want to call it a washer, delta A is going to be approximately, what will it be approximately? We talked about this already. Get your scissors out. Cut the circle, unroll it. So it looks like a long and thin rectangle. It's not a rectangle, it's technically a trapezoid. But if delta R is small, that is going to be the width of the thin ring, by the way, is delta R. If delta R is small, the area of a rectangle looking about like that will be the same as the, or approximately the same as the area of the ring. What's the width? 2 pi r, the circumference of the circle. Which of course is a little confusing because there's 2 circles. Which one? The point is it doesn't matter because delta r is so small that effectively you could take the inner circle or the outer circle. And you don't even really need to specify which radius r represents. Because remember, we're really trying to just set up the integral. And in the integral, you don't care about which one it is. That make sense? Technically speaking, you could say it's the area of the outer circle minus the area of the inner circle. You could use the formula for the area of circles and subtract. And you'd get a squared term. In fact, you get delta r squared in there somewhere. But if delta r is really small, delta r squared would be really small. Like if delta r were 0.000001, what's that? 10 to the negative, what? 1, 2, 3, 4, 5, 6, 7, 8 or something. If my eyes are not deceiving me. 10 to the negative 8 squared is 10 to the negative 16. Which is, I hope you realize, 100 million times smaller than 10 to the negative 8. So delta r is small, delta r squared is really, really small. It's negligible. And because of that, that turns out to be another reason why we can take this to be approximately 2 pi r. I'm not giving you details. I think the book does. They give you details in one spot at least. So delta A is approximately 2 pi r times delta r. Use this now. That means delta P, P for population, population in thin ring, population instead of a mass this time. It's approximately delta of R times delta A. Right, this is in people per square mile. This is in square miles, and the square miles would cancel, giving you units of people. And that'll be the same as replace delta A with this, 2 pi r delta of R times delta R. Lots of deltas here. Delta of R is a function. Delta R is a small number. The total population of the city then, you could call it just P, is the sum of the small populations in the thin rings, which is going to be approximately the sum of expressions like that, 2 pi r delta of R times delta R. And then the magic happens. Let delta R go to 0. The summation sign morphs into an integral sign. The delta r morphs into a dr, and we end up integrating that function, 2 pi r delta r dr. And again, this magic, this morphing is just pretend for fun. It's really nothing special, actually. It's really a definition. It just feels special. Well, okay, it is special still. It's special because integrals themselves are special, but it's nothing magical truly going on. Just rigorous math that's being hidden. This is not rigorous math here. This is hand-wavy math, right? Don't ever think this is a rigorous argument. That was my problem. I was in my physics classes, for example, and my teachers were doing this. I'm like, how do you know you can do that? And they're like, what are you, a mathematician? I'm like, I guess I am because I'm a math major. And most of them know they're not doing rigorous math, but what they would say is it just makes sense. They wouldn't say it's perfect logical deductions. They just say it makes sense. It makes intuitive sense because they've done it enough. You do need limits of integration, though. Always remember that. R is a radius from the center, so R goes from 0 to 3. Not -3 to +3, from 0 to 3. Because we're slicing with circles here instead of vertical slices or something. We would not want to slice with vertical slices because the density function depends on the radius. In multivariable calculus, you could have a density function that depends on just location. And then you'd actually want to slice into small little squares, and you'd want to do something called a double integral in the end. And if you take multivariable calculus, you will do that. R goes from 0 to 3. Now plug in the function delta of R. It was what? 10,000 times 3 minus R. Factor out the 2 pi and the 10,000 to get a 20,000 pi out front times the integral from 0 to 3 of, I'll distribute the R through here, 3R minus R squared. 20,000 pi times 3/2 R squared minus 1/3 R cubed from 0 to 3. Plug in 3, get 27/2, right? 3 squared times 3 is 27 over 2. 3 cubed over 3 is 9, which is the same as 18/2. 27/2 minus 18/2 is 9/2. This 2 can cancel with the 20,000. Looks like it's 90,000 pi is the population, people. Of course, you would not want to leave such a thing in terms of pi. So the nearest whole number, 90,000 pi, is about 282,743. You know, that's way too many significant digits. How many significant digits is right? It kind of depends on how accurate the modeling is. So we can't really say exactly how many significant digits is right. It seems reasonable to me to round this to say 283,000. That would be a reasonable thing to do. Perhaps more reasonable would be 280,000.